ready. Okay, so the first thing I want to do before we start continuing with physics is address a problem that actually I sent to everybody. Not many of you took me at my word and answered, but at least I got one answer, and that answer made me reflect a lot. So then I want to discuss it. And that was the problem, if you remember, the wager or the discussion between Pascal and Fermat. That they were playing, Chevalier de la Mer wrote a letter to Pascal asking him, what do you think about this problem? Two people are playing, I remind you the facts. I win by getting the number 1. I win. Who was the other? Bar. Bar wins by getting the number 2. And if we get 3, 4, 5, or 6, we throw it out. If we get any of these, nobody wins. Okay, and the game is the first person who we throw once, and then again, the first person to get his number twice wins. And of course, you can have a short game or a very long game, but he said that for some strange reason, the game stops when I had gotten my number 1, and he hadn't gotten yet his number any time. But we have to stop the game, and then comes the issue of how we divide the prize. Because one alternative is say, well, the game didn't finish, so 50-50. The other alternative, which is what I would argue, is I am on the lead because my number came 1, so I am more likely to win than you. So I should get the money, and we said that the fair thing, that's what Pascal and Fermat were arguing about, was, well, we should split it according to the chances of each of us to win. And so that was the problem, determining if the sequence, now I already won 1, so if one time the number 1 comes, I win. If before that 2 times the number 2 comes, he wins. And we have to keep playing. What are my chances? What are his chances? So I set the problem, and I got one solution. I got one student solution. So first let me tell you the solution that Fermat and Pascal came up with in their correspondence. So I will call this the Fermat solution, which is the most elegant for reasons, or it was the most elegant for a few centuries. So that solution said the following. He said, well, in the next throw of the dice, there are 3 possibilities. With probability 1/6, I win. With probability 1/6, I get my number. With probability 1/6, Bart gets his number, and with probability 2/3, nobody gets their number. Those are the only 3 possible outcomes. So he said, I said, how can I win? I am trying to calculate X, the probability of me winning. So, and there are 3 ways I can win. I can win by this being the next throw of the die, or this being the next throw of the dice, or this being the next throw of the dice. One of the 3 has to happen. So let me calculate the probability of me winning if this happens, or if this happens. And I will sum the 3, because these are 3 disjoint events, because one of these 3 has to happen. So first, the probability of me getting the number 1. What is the probability of me winning, knowing that I got the number 1? 100%, right? Because I won. So this goes multiplied by 1. Then the probability that he gets his number. What is the probability that I will win, knowing that he gets his number now? Now we are tied, right? So I am as likely as win as he is, because we both need to get our number, so it's 1/2. So if he wins, the probability is 1/2. If nobody wins, so we get some other number, what is the probability of me winning? Is X again, right? Because X is the probability when I am 1 turn ahead. The X I am calculating appears here again. So this is an equation for X, and this equation is very easy to solve. Move this to this side, you get X over 3 is equal to 1/6 plus 1/12, which is 1/4. So x is 3/4. So my probability of winning is 3/4, and you can do the same equation for the probability of his winning, and you can get 1/4. So that's what Pascal said, very good, and I like it. Not only that, Bart took the trouble of actually playing the game. He took the computer and he told the computer, throw a dice as many times as necessary until one time the number 1 appears, or 2 times the number 2 appears, and he did that 50,000 times, and in 75% of the times, I won. So experimentally, we know that this is the right solution. So, but that was cheating, because I looked at the nice solution of Fermat. So then I came with my solution, which is not as elegant as Fermat, but at least I did it myself, which is nice, and I said the following. How can I win? So this will be the quick solution. Okay, I said, how can I win? Well, either I win in the next throw of the dice, or in the second throw of the dice, or in the third, or in the fourth, or at some point. But at some point I win. What is the probability of me winning and these are all disjoint events. I either win in the first, or in the second, or the fifth, or at some point. What is my probability of winning in the first one? 1/6. That's simple. What is the probability of me winning in the second one? Well, in the first one, something else has to happen with probability 5/6, so that my number doesn't come, because if not, I win in the first. And this multiplied by 1/6, which is the probability that in the second one I win. So this is the probability of winning at the first attempt. This is the probability in the second attempt. Now, what is the probability of the third attempt? That's when it gets interesting. How can I win in the first attempt? There are two ways. That in the previous 2 attempts, the numbers that came were the 3, 4, 5, and 6, and that well, first of all, the probability of not winning in the first 2 multiplied by 1/6. It's always by the probability that in the attempt number 3 I win. So, and the way of not winning in 2 attempts are 2 ways. Either in the 2 games, nobody wins, which is this probability, or he wins once, and once another number comes. Because if he wins twice, I cannot win. So, how are the ways in which one time Bart gets his and another gets and the other not? It's 2/3 for the time in which he doesn't win times 1/6. And I have to multiply this by the number 2, because there are 2 events. He winning the first one and nobody winning the second, or he winning the second and nobody winning the first one. So there is a factor 2, okay? And you can do the math, I don't care how much that gives me. But, this can be generalized. What is my probability of winning in an attempt number n? It's the same idea. Is the probability of actually in the throw number n, I get my number, multiplied by the 2 only ways in which in the other n-1 event nobody wins. Either n-1 times in a row nobody gets the number, with probability 2/3 to the n-1, this being the case n equals to 3, or to have a sequence in which n-2 times comes the number 3, 4, 5, and 6, and only 1 time comes the number 1/6. So it's 2/3 to the n-2 times 1/6, and multiplied by the number of places in which his win can happen, which is in any of the n-1. So this is the way of me winning in attempt number n. You can check this formula, that if you replace n by 3, you get this expression. That if you replace n by 2, you get the expression that is above. Oops, I went too far. If I replace n by 2, this goes away. I have 1/6 plus 2/3, which is 5/6 times 1/6. And if I replace n by 1, this goes away because I have n minus 1. This gives me 2/3. To the 0 is 1, so it's 1/6. So this formula works for all n bigger or equal than n. So the probability of me winning is the sum of this when n goes from 1 to infinity of this expression. 1/6, 2/3 to the n minus 1, plus 2/3 to the n minus 2, n minus 1 over 6. You sum this, and believe me, you get the number 3/4. If you don't believe me, well, I have two answers for you. If you took the course in modern with me, you learn how to calculate the sum of something to the n, and n times something to something to the n. So you know how to do it. If you took the course in networks last semester, you also learned how to do these sums, so you know how to do it. If you didn't take either of those courses, that's your problem. You should choose better your schedule, but you can learn it. Learn it, try it, because in a month, when we get to the Boltzmann distribution, to the Planck distribution, you will need to know how to do this sum. So if you cannot do this sum, ask me later. Try it and ask me tomorrow or whatever. But this is an harmonic series, okay? So it's 1 over 1 minus 2/3, etc. You do the math, you get 3/4. So the query solution is much longer, much less elegant, but it works. So now comes the third solution. And the third solution is the solution submitted by Barr, the Aluf solution. And this has one problem. Let me tell you a secret you don't know. When, and if you teach physics 1 many times, this happens, that the student has no clue of what he's doing, he mixes 3 constants, and he gets the right answer, and it's clear that he has mixed numbers that cannot go in the same formula, make no sense, and gets the right answer. That makes any professor concerned, because they say, why do I even bother if they can guess the right solution doing something stupid and getting the right answer? That, if they get the wrong answer, I'm happy. I fail them, I get on. But they get the wrong answer, the right answer, doing something wrong, that's unacceptable to me. So look the Aluf solution. The Aluf solution is the following. He says, well, 1, the professor wins, 2, I win, 3, 4, 5, and 6, nobody wins, so who cares? Let's ignore those numbers. So let's assume that every time, only the 1 or the 2 can come up, and all the other numbers can never come up. And let's do that game. Well, now you agree that the game is very simple, because in the first row, either he gets, I get my number and I win, or he gets his number, and now we are tied, and in the second throw, one of us wins. Okay, so the game lasts exactly 2 times, because now there are only a few choices. Let's calculate the probabilities of he winning. It's very simple. He has to get his number the first time and the second time, so the probability is 1/4, because now each one has 1/2. His probability is 1/4. What is mine? That I win in the first time with this probability, or that I win in the second time, which is that he wins in the first time with probability 1/2, and I win in the second with probability 1/2. So 1/2 plus 1/4 is 3/4. So this is much more elegant, and it's completely wrong, because obviously, why would you do that using only 2, and why are you not considering, and you are simplifying this? So this was a lucky coincidence, right? So when I saw that, I said, this is, he has no right of getting it right, doing something so simple that you can do it in a step. He's smarter than me, but he's not smarter than Fermat. So then I said, okay, let me think. Let me think what happened if Fermat, instead of playing with a die that has 6 possibilities, would play with a die that has 20 possibilities, or 15 possibilities, or 9 possibilities. Imagine that he has D. So let me go back to the Fermat argument and try to repeat it, but this time, okay, let me look here if I can do it without writing everything. But let me repeat Fermat argument, but instead of using the number 6, using the number D. So I win with probability 1 over d, Barn wins with probability 1 over d, and nobody wins with probability d minus 2 over d, right? For d equals to 6, we get that answer. So if you repeat this argument, what would you say? The first result happens with probability 1 over d, and in that case I win, for sure. The other case also happens with probability 1 over d, and in that case we are tied, and so the probability of me winning is 1/2, and with probability d minus 2 over d, the game repeats itself. So we won once each, so it's the number x. So this is the question. Instead of this equation, you solve that equation. You solve that equation, guess what happens? The d drops, and you get 3/4. So the d doesn't matter. So just do it. Do the algebra, and all the d's cancel, and at the end of the day, you get the same. So then I went and I did the Quillet solution, doing the same thing, replacing all my 6's by d's. So I did all this formula. I'm not going to bother you with all this. I did those big formula assuming that there are d possible results, and I win with chances 1 over d each time, and he wins with chances 1 over d, and with chances d minus 2 over d, nobody wins. And you do all this series and you sum them, and you get 3/4 or 1/4. So the answer is that it doesn't matter. As long as in the game he and I in any given throw have the same chances, doesn't matter if there are 2 chances or 6 chances or 20 chances, or doesn't matter. So his method that it seems so silly is actually right, because if d doesn't matter, well, you might as well use d equals to 2, which is the easiest case, that you are flipping a coin. And indeed, his method, so I had to, eat crow, as they say, and it worked. So there you have. So you always learn something simple. I have not looked at the correspondence between Pascal and Fermat and see if they foresaw that, or they speculated on that, or somebody else did it, and perhaps it's a triviality, but I liked it. Because when he got it, I said, this is clearly wrong, and I have to see where he got wrong. I said, if I try for another number that is not 6, I am sure this will not work. And then I found out that this works always, doesn't matter what d is. So that's interesting. So that was one thing. So this is a sort of apology, because I screamed at you the other day for getting it, and now I see that you could have done it. Okay, so that's what's an aside, but since you're starting to do some calculations in probability, perhaps it's useful. Some of these things might be useful. Oops. Okay, now I am going back to what we're discussing. Remember, what is it that we discussed last time? We took the following model, a model of picking up spins that can be up or down. Any given state of the system is a collection of arrows that can be up and down, and there were 2 to the n possibilities, and we started grouping them by the excess spin. How many? Assuming that there might be a magnetic field that would make a difference, because in the case of a magnetic field, the total energy was minus 2m n up minus n down, and I call this number n up minus n, I call 2s, or something like this. So we try to calculate how many microstates correspond to each possible configuration. And we got this number, G of ns. S is called, the 2s is defined as n plus minus n minus. And we got this number that tells me how likely these states are. And this number was, I remind you, well, I have it here, square root of 2 of the, in the Gaussian approximation, and then we'll comment more on that later, is this number e to the minus 2 squared over n. So the maximum is when s is equal to 0, and it decays, and we learned some interesting things, that this decays so fast that if n is a very big number, a number of the order of of 10 to the 22. The most likely state is when you have exactly 50% of the spins up and 50 down. It's a little smaller, the probability of having 50% plus 1 up and 50% minus 1 down, etc. But when you go to the probability of having one spin every billion pointing away from 50-50, the probability of this was extremely small, was essentially nothing. So of all these possible states, they were overwhelmingly dominated by the case 50-50. That's what we learned here. Okay? If you want to describe this as a probability to make contact with what you know from before, you would say that the probability in a state of n spins of getting excess spin s, we will call this g of ns divided 2 to the n, because remember, we showed that the sum of all of those is 2 to the n. So the probability is the total number dividing the normalization constant. Now, if we sum all these probabilities, we get the number 1. Okay? So this is what we found out. This is the distribution of spins up and down here. When we count how many of them actually, what is the probability of having an excess spin, number of spin up minus down, s. And I said at the end of the class that this could be used to something a little more physical than that, which is a famous problem that has been studied for a long time in probability, which is the random walker. A person who is standing here flips a coin, and if it's heads, he gives a step in that direction, and if it's tails, he gives a step in the opposite direction. And he keeps doing that for n steps. And so you see immediately that his final position, let me call m the final position, is m plus minus n minus. If you give as many, so one state is right, right, left, left, right, left, left, whatever. Okay, at each stage, I have this. You see that it's exactly the same problem. Only that now, this, which happens to be what I call 2s, is now the final position of the random walker. So we can translate what we learned before in terms of the random walk. So we calculated before that the average value of s was 0, means that the average value of the final position, which is the average value of 2s, is the number 0. What does it mean? That if Bar programs again flipping a coin and going and he launches a random walker who gives 10,000 steps, 50 with probability 50-50 in each direction, and he records the final position, and then he does it again, and he does it again, he does it 1,000,000 times, and he averages the 1,000,000 final positions, he will get a number very close to 0. That's what we learned. The random walker in one dimension, the average value of his final position is 0. But we learned something else, which is much more useful. We learned that the fluctuations on this number, the fluctuations on 2s, so this is what we call the fluctuations, right? The average, no, sorry, the average value of 2s squared, which is 4 times the average value of s squared, and we showed that this was n over 4. So the fluctuations in the final position is the number n. So that's a very powerful result of the theory of random walk. That you have a random walker. Again, we asked Bart to do the experiment, but now each time when he finds the final position of the random walker, instead of storing that number, he stores the square. And he does it again, and he does it again, and he does it 1,000,000 times, and he averages the final position over 1,000,000 runs, he will get n, the length of the walk. Okay? That means that the average distance moved by the random walker, which is the square root of this, goes as the square root of n. So this is quite an important result in the theory of diffusion. Anyone who had a course, probably differential equations, if you solve the Fourier equation or whatever, you have seen that. Whenever you have random steps, the distance that you will move goes as the square root of the number of steps you take. What does it mean? This is a beautiful experiment that I saw it done in a classroom. It requires better conditions than here, which is doing the following. Typically, a random walk is what happens when you launch a molecule here and moves in this room, because it gets hit from one side, from the other side, and it moves at random. Of course, it's not a random walk in one dimension, it's a random walk in 3 dimensions, but the mathematics is the same, that the square distance you move goes as the number of steps. So imagine that the number of steps is proportional to the time. Each millisecond, you are hit by someone. So the distance that you cover on average goes as the square root of time. That's a result that people in random walk theory know. That's, if you, instead of going straight in the ballistic way, you go randomly, the distance you cover in any particular direction goes as the square root of the time. That means that if you want to go 4 times further, you got to go twice as far, you need to wait 4 times more, not only 2 times more. So the experiment I was saying is you open a little flask of a perfume that is very intense, and you do it in one end of the classroom, in a very big lecture hall, and you ask people to raise their hand when they can smell it. And normally the people who are in the first row, who are 6 meters away, will smell it after 10 minutes, but the people who are 12 meters away will smell it after 25 minutes, 4 times more, and you can actually plot how the molecule moves just by seeing when anyone can detect it. Because you need enough of these molecules to come to your nose for you to detect it. Of course, it's a simple way of showing a random walk, but actually you can do it in a computer. You take random walks, and instead of averaging the final position, you average the square of the final position, and you will see that it goes like n. So the average mean root, what we call the mean root displacement, which is this, is proportional to square root of n. That's a beautiful result, so I wanted to put what we learned last time in another line. And what I want to do now is to show you that in this case, the simplification that allowed us to solve this problem quite easily was based on 2 things. And the 2 were here present, but only one of them was very important. The one that was very important was the fact that every single possible result was there with the same probability. So the up, down, up, or the up, all of these, because each one can be in any state, so all the 2 to the n appear with the same probability. This will be a crucial statement later on, that all these probabilities are equivalent. So when we got how many states correspond to, say, 4 spins up and 1 spin down, if you want to know the probability, all we did is divide by 2 to the n. That was one of the big simplifications. But there was another thing that made this, yes?
That statement is only true because there's only 2 possibilities.
Yeah, because it's a binary system and all possible states are equally probable. But there is another state that was happening in this model that it happened here, but we didn't need that, which is the fact that the probability with which one spin points up or another spin points down was 50-50. So when we picked all the configurations, any of these configurations were equally probable. That, I mean, we can have it, but we cannot have it. We can decide that a spin will point up with probability P and will point down with probability Q. Now, obviously, this state will not have the same probability as this one. But the results we obtained of counting how many ways there are of having, that has nothing to do with that, okay? So it is true that now not all of them are equally probable, but how many correspond, how many micro configurations correspond to a macro is independent of that. So I want to show you in a model that if we do that, and this is a very usual step, is a random walker that instead of moving to the right or to the left, flipping a coin with probability 50-50, has a step to the right with probability P, and a step to the left with probability Q, P plus Q being 1, of course, but these two numbers are arbitrary numbers. So for example, at each step, he has 4 times a bigger chance to go into the right than to the left. This is 0.8 and this is 0.2. That's another model. And we can do exactly the same. And we can do everything the same because you see, in this step, where you end up has nothing to do with the probability. Where you end up, we said, is the number of steps to the right minus the number of steps to the left. Okay? Is call it n plus minus n minus. That tells you where you end up. That has nothing to do with the configuration. So you see, any configuration that have 3 spins up and 2 spins down will contribute, say, to finishing at point 1, because 3 minus 2 is 1. All those will contribute, and that doesn't change the fact that now each of them has a different probability than this one, because this one has probability p to the 5th. Okay, it's not 1 over 2 to the 5th, as before. It's p to the 5th, which might be much bigger. If p is 0.9, this is much bigger. If p is 1, this is the only thing that can happen. But still, there is only one way. And in this case, 4 up and 1 down, there are 4 ways. And that is a fact that remains there. The probability is, of course, p to the 4q, which can be a number that now is, again, depending on who p and q are, can be much or smaller than 2 over n. But there are still 5 of those. Okay, so I want to consider that model now. And everything we said before will still be valid, only that the probabilities of the different steps are not the same. But you see, if I want to calculate now the probability of, say, a given step, let me do a simple example. Let me assume that n is 8, so I have a random walker that will give 8 steps. And I'm calculating the probability that m is equal to 2, that he finishes at position m equals to 2. This can happen in one way and one way only, that you have to give 5 steps to the right and 3 to the left. Because, remember, n plus n minus has to be the number 8. And n plus minus n minus has to be the number 2. And the only way that this happens is if n plus is 5 and n minus is 3. Okay, just solve these 2 equations. So the probability of this is all the ways, of course, that you have of doing a random walk with 5 steps to the right and 3 to the left, and 3 to the left, which is the combinatorial 8-5. You know, of the 8 steps, I choose where are my 5. Only that now, instead of each one being multiplied by 1 over 2 to the n, each one is multiplied by p to the 5, q to the 3. Okay, this is the only difference. But this combinatorial is the same as before. That didn't change. What changed is this factor. Yes?
So the combinatorial n over n minus r the same as n r?
Yeah, absolutely. The combinatorial 8-5 or 8-3, because the combinatorial is 8 factorial over 5 factorial, 3 factorial. Yeah, 8-5 or 8-3s are the same combinatorial. So you see, so if I want to generalize this, what I will say is the probability of Pn getting the value m. What is the probability that in the random walk of n steps I end up at position m is the probability of getting the combinatorial n factorial over n plus factorial and minus factorial multiplied by p to the n plus q to the n minus. Okay? Or I might choose to write this as n over 2 plus s and this as n over 2 minus s, as we did before, and the same here. So I can express it if I want in terms of n plus and n minus or in terms of s. But it's essentially that. But you see, this is the probability of me ending there and remembering that this is for that particular case. M is who? M is n plus minus n minus, or is n plus minus the number n minus, which is n minus n plus. Okay? So this is 2n plus minus n. So I can work in the variable n plus, but at the end of the calculation I have to remember that the m I am interested is twice n plus minus n. And I can replace at the end of my calculation if I want to calculate any probability. So, first of all, convince yourself that this is a very well-defined probability. How do I know that? I sum over all the possible values of m, and I need to get 1. If not, that's not the probability. Okay? So, if I sum, m can take which values? Can go all the way from minus n over 2 to n over 2, as usual. Or n plus can go all the way from 0 to n, because I can have a walk in which I have not one single step to the right, one step to the right, and all the others to the left, 2 to the right, etc. So if I sum this when n plus goes from 0 to n, this number, sorry, without that, this should give me the number 1, and you can convince yourself that this is the case, because this is Newton's binomial for p plus q to the n, right? You all recognize that this expression is Newton's binomial, and p plus q is the number 1. So this is a well-defined problem. But this problem doesn't have the symmetry that my other problem had. In the other case, the chances of all the spins pointing up and all the spins pointing down had the same probability, because there was only one way of all the spins pointing up, only one way of all the spins pointing down. Since each one had probability 1 over 2 to the n, they both had the same. Now, all pointing up will have this probability, p to the n. And all spins pointing down, or all steps going to the left, will have probability q to the n. And this number need not be different, need not be equal. If p happens to be 1/2, we are in the previous case. Then these and these are the same. But if p is 0.9, well, obviously the probability that I end up going straight steps in one direction and I end at position n are much bigger than I go in the other direction. Okay? And if p and q are 1/2, the most likely thing, it's as likely that I end up all the way to the right and all the way to the left. You see, I wanted to show you this because this obviously will have something different. Before, we had that the average value of s was the number 0. Okay? This will not be the case here anymore. Okay? Imagine if p is 1, means that every time I walk all the way to the right. Obviously, the final value will not be 0. Because if every time I do it, I end up at position n, the average final value will be n. So s will not be 0, but now we can calculate it. So let me calculate these things with this new, since we know the distribution, we can calculate that. So I will calculate the average value of n plus, and then replace by what I showed before, that m is nothing else than 2m plus minus n. So if I calculate the final value of this, the final value of m will be twice the average value of n will be twice the average value of n plus minus n. Okay, so let me calculate that. This is, by definition, is the sum when n plus goes from 0 to n of the combinatorial n now I need to write combinatorial explicitly. N factorial, n plus factorial, n minus n plus factorial, p to the n plus, q to the n minus n plus. This is the probability, but since I need the average value of this, I need to multiply each term by the quantity n plus. Okay? Let me write it in another color so you see. Because I am calculating the average value of this, so I have to multiply this by the probability with which each step is taken. You all see this. This is what I define calculating a probability. I multiply the number I want to average times the probability of each state, which is what's there in red. So how does this sum go? We did it a few times, but let me do it once again. These two numbers cancel, so here I have n factorial on the bottom, n plus minus 1 factorial, because I have a factor n plus, n minus n plus factorial, p to the n plus, q to the n minus n plus. And now I will do the following trick. I have to do this sum, and I have to make the sum in any simple way. First of all, I observe that in this sum I don't have to include the term equal to 0, because I have these cancels, so the sum starts from 1. The sum starts from 1 to n, and then I can do the following trick. I take out the factor n, and I take out the factor p. So this will be p to the n plus minus 1. And this, instead of being n factorial, will be n minus 1 factorial. Okay? Because if I take a factor n, I get a factorial. And now you can see where this is going. Just do a trivial change of variables. N plus minus 1, call it, I don't know, n prime plus. So you get np times the sum of a new variable that runs now from 0 to n minus 1 of what? N minus 1 factorial is on the top. The new variable n plus prime factorial, and here I have n minus 1 minus n prime plus. Okay, because I subtract 1, I have to subtract 1 here and 1 here. For nothing to change. And here I have p to the n prime plus, n plus minus 1, I call it n prime plus, and here I have q to the n minus 1 minus n prime plus. And if you stare at this expression is the Newton's binomial of p plus q to the power n minus 1. Okay, it's p to the something, q to the n minus 1 minus that something, and here I have the factorial of n minus 1, and the factorial of the something, and the factorial of n minus 1 minus the something. So all this sum is p plus q to the n minus 1, which is the number 1. So the average value of n plus is np. The average value of n plus is the number np. Makes sense. If p is 1/2, the average value of the number of steps I will give to the right will be n over 2. But if p is bigger, the average value will be bigger than n over 2. And if p is smaller, the average value will be smaller. So the final position, which remember was twice the average value of n plus minus 1, this is the average final position, is twice np minus 1. Or No, when minus n, sorry. This was the number. Twice this minus n. So it's n times 2p minus 1, or this is the same as n times p minus 1 minus p, which is q. So the final position, this is a well-known result, is n times p minus q. If p is equal to q, is our old result. The final position will be at the origin. But if p is bigger than q, the final position will be to the right of the origin on average. And if p is smaller than q, the average position will be at the left of the origin. So, before, average m was 0. Now, this was before. Now, it's this. So, this is the change between a random walk and a biased random walk, in which I move in one direction. Let me, before I calculate the fluctuations, which is the other interesting quantity I want to calculate, show you that this result can be obtained in a cheaper way. And we always need cheaper ways, and we will need it. So I need to do the sum from 0 to n of the combinatorial n plus, remember, p to the n plus, q to the n minus n plus, and I had to multiply all this by n plus. Remember, that was the whole story. That required me to do all this change of indices and so on. You can save a lot of trouble if you do the following simple observation. That n plus times p to the n plus is exactly this, which is what I have here, n plus times p to the n plus, is the same as writing p times the derivative with respect to p of p to the n plus. Okay, when I take the derivative, I get the factor n plus, and I get p to the n plus minus 1 times the p, I get p to the n plus. So this can be written like this. So this expression can be obtained from p to the n plus just by using this. Okay? Then let me do that trick here. The sum from 0 to n, of the combinatorial n plus times n plus p to the n plus, which we say is p derivative with respect to p to the n plus, q to the n minus n plus. And now what I do, obviously, is I take this derivative and I take it out of the sum, because I am summing over n, I am not summing over p. So I get p derivative with respect to p of this expression, the combinatorial n plus, p to the n plus, q to the n minus n plus, which is, we know this is p plus q to the n, right? So what I get is p times the derivative with respect to p of p plus q to the n. And only at the end of the calculation, I say that q happens to be 1 minus p. Because if I put it now, obviously I get nothing. So I do this derivative, and then when I'm done, I replace q by 1 minus p. So what do I get here? I get n times p times the derivative of this, which is p plus q to the n minus 1. And that's the end of the calculation. So now I replace q by 1 minus p, or this is 1, I get np. So you see, instead of doing sums, I just take a derivative. Why do I tell you that? Because if I want to get the fluctuations now before I calculated the average value of n, through calculating the average value of n plus. Now, so the average value of the final position. Now I want the fluctuations of that. I remind you, for those of you who didn't have a formal course in statistics, we call the delta of some quantity is the quantity minus its average. So how much any number differs from the average. And what we call the fluctuation, delta x squared, is the square of this number, obviously, so it's x to the square plus average of x to the square minus 2x average of x. And so what we call the fluctuations or the variance of the quantity x is the average of that number. So I need to take the average of this is what I call the variance of the quantity x. I take each value of x, I subtract the average, I square, and I take an average. And when I take an average, I have to take an average here, here, and here. And that's quite simple, because here is an average. Here I have to do nothing, because this is already a number. The average of something is a number, so there is nothing to average. And here, there is nothing to average here. The only place where I average is here. So if you look, what do I get? The average of x squared plus the average of x to the power 2 minus twice the average of x to the power 2. Or, in other words, the average of x squared minus the average of x to the square. This is what you learned in the first class of the course in probability. That the fluctuation of any quantity is just the average of the square of the quantity minus the square of the average of the quantity. I am just reminding you this in case you didn't have a course in probability, but this is what you care the most. So if you need to calculate the fluctuation of any quantity or the variance of any quantity, what you do is you calculate the average of the square of the quantity and you subtract the square of the average of the quantity. So what does it mean in our case? Delta m is m minus m average, right? By definition. And that is 2n plus minus n minus 2n plus minus n. Okay? This number minus the average of this same number, which, as you see, the n and the n cancel, and you get twice n plus minus n plus average. So the delta m is twice the delta of n plus. That means that I don't calculate delta m, I calculate delta n plus. And to calculate delta m squared, which is what I care about, I calculate 4 delta n plus squared. Okay? So I have to calculate the variance of n plus and just multiply by 4. So I need to calculate this quantity, delta n plus square average. Okay, that's my statistical calculation. And what is that? As I said, this is n plus squared average minus n plus average squared. Okay? And this number I already calculated. This was NP. So I need to calculate this. So all I have to calculate is the average of n plus squared. You see why I wanted to use this operator, because what I have to calculate now is the sum of n plus combinatorial, p to the n plus, q to the n minus n plus, but the whole thing multiplied by n plus squared, because I'm trying to calculate the average of that quantity. Let me underline that. since I am trying to calculate just this term I know what it is. This term is np to the power 2. This term I already know. This is the one I need. So I just have to put the np squared, and you see why I did the trick I showed you before. Because n plus times n plus p to the n plus is, from what I said before, is n plus p derivative with respect to p of p to the n plus. And if you put this inside, you get that you get p times the derivative with respect to p of n plus p to the n plus. And this is nothing else than p derivative with respect to p of p derivative with respect to p of p to the n plus. So you see, the fact that I have n plus square now means that I have to use this operator twice. And using the operator twice, all it means is that in my long sum, I have n plus combinatorial, p to the n plus q to the n minus n plus, and I have outside p ddp, and again p ddp. So I have this operator twice. And since this sum I know how to do, this is p plus q to the n, means that all I have to do is p derivative with respect to p twice of p plus q to the n. And you see, once I did it already. The first time, or well, let me do it. The first time that I operate, I get p derivative with respect to p of this, which we said was np p plus q to the n minus 1. Remember, we calculated that the derivative p times the derivative of p is that. So I have to apply this again. Did I do it somewhere? Yes. So I have np. Didn't I make any mistake? No. So far, so good. So when I take the derivative, let me pull the n outside and the p, this one outside. I take the derivative. I get two terms. P plus q to the n minus 1, and I derive here, plus p n minus 1, p plus q to the n minus 2. And now that's the end of the calculation, right? Did I get it right? Np, n minus 1p. Yes. Okay, and now I replace at the end of the calculation p plus q is the number 1. So what do I get? Np times 1 plus n minus 1p. So that's, finally, this is delta n plus square average. No, this was, sorry, this was, whoops, I went too many times. Can you push it back? Oops, move it forward. One more, and this, okay. I'll put a very long page here, I believe. Okay, well, I'll stop here. So this is something else. This is n plus squared. So I was calculating n plus to the power 2 squared. So, and remember, so let me finish the calculation here. So the fluctuations in n plus, remember, was this minus the average value of np squared. So I have to do, let me just correct this and make it a little nicer. This is np 1 plus n minus 1p, that's correct. This I can write even easier as NP times, I am just simplifying here, I have another factor NP times 1 minus P, which is plus 1 minus P, which is Q, P plus Q. So now this is very good, because then the fluctuations are this number minus NP squared. So this cancels, and I get NPQ, cubed result. Okay, because I have to, from this, subtract NP to the power 2, which is this first term. And you see, this is totally correct, because when P is 1/2 and Q is 1/2, I get N over 4, which was our old result. That the average fluctuation in N plus, or in S, in N plus, was N over 4. That means that the average fluctuation, or the variance, if you want, in M, remember, was 4 times this, is 4 NPQ, or in the case of the symmetric random walk, is the number N, because P is 1/2, Q is 1/2. So I got finally all the results. So let me collect the results and stop here. The average value of N, the average value of the final position of the random walker is this. And the variance in that value is 4 NPQ. And you can check, as I said before, when P is equal to Q equals to 1/2, we get the old results, because this is nothing else than 2S. Okay, so now you know what happens with a random walker in a biased random walk. He will end up to the right or to the left of the origin, depending on in which direction the walk is biased, and the fluctuation will be this. You see, it makes sense. Imagine that P happens to be 1 and Q happens to be 0. What is the final value of the final position? It's just the number N. Because if you always go to the right with probability 1 and never to the left with probability 0, you're always with N. After N steps, you will be at position N. And the fluctuation will be 0. If this is 1 and this is 0, you get 0. If in every single attempt you get the same number N, the fluctuation is 0, because the deviation from the average is 0. 0 squared is 0. If every time you get the same result, the fluctuation is 0, or the variance. I use the word fluctuations because physicists call it fluctuations. A mathematician will call it the variance of a quantity, but it's the same thing. Okay? Even one more step, if we want to calculate the relative size of the delta M root mean square, which is the square root of that. Remember, the root mean square is the square root of the variance, is 2 square root of NPQ. Okay, it's the square root of that number, which means that delta M root mean square over the the average value of M is this over NP minus Q, 2 square root of NPQ over NP minus Q. And this sometimes is simplified the following way, just by writing, how did I write it? That's the same thing, yeah, okay. If I want, instead of that, to write the root mean square of N plus over the average value of N plus, which perhaps is a little more intuitive, what did I get before? This was the square root of NPQ, right? Without the 4, and this is NP. So all this gives me square root of Q over P times 1 over square root of N. Remember that before we found that the average of the fluctuation divided the length of the quantity was 1 over square root of N. Here is the same times this factor, which will be 1 in the symmetric case. Okay, so this is as much as I want to say about a random walk which is biased. I want, before I start making connections with statistical physics, to do two more things. That will not take me too long, but I might do them after the break. One is to show you, but let me at least tell you what I'm going to do. One is to calculate a very important limit in probability. Those of you who took it in course of probability did it, which is phenomena like this, in which instead of considering the situation we considered at the beginning, when P and Q were numbers of order 1/2 or similar to 1/2, 0.6 and 0.4, when you have P extremely small number and Q very close to 1, but N is so big that the product N times P has some finite value, say lambda. So N can be 1,000,000 and P is 10 to the minus 5. And Q, of course, is almost 1. It's 1 minus 10 to the minus 5. This is called the Poisson limit. So we'll study that because that appears a lot, particularly in physics. The other thing I want to do is to show you that actually this Gaussian approximation, here we were working with exact binomial distribution. But last time we did a Gaussian approximation to this, where we got e to the minus s squared. I want to show you that this is nothing else than taking the real distribution and expanding to second order. If you do that and you expand to second order, nothing else, the way you would expand any mathematical function, you get precisely this Gaussian approximation. So the Gaussian approximation is nothing else than the second order expansion of a real binomial distribution. So we'll do those two things after the break, and then we move to a little bit of thermodynamics, well, not thermodynamics, statistical introduction of the thermodynamic concepts. Okay, good. So you want to stop it?
Yeah.